Hello friends, welcome to this lecture on implementation of queue using arrays. So in this lecture, we will be looking at implementation of queue data structure using arrays. So if we look at exactly the topics covered, so first we look at introduction, wherein we will see that if you're implementing queue using array, it is more efficient approach as compared to implementing queue using linked list. So that's a very interesting point I'm discussing with you. So that in detail we will discuss in this introduction. Then we'll look at naive array implementation. So naive array implementation is basically the linear queue. We'll be implementing linear queue. Then we will look at efficient circular queue implementation using array. Then we'll compare the time complexity of both these approaches, like linear queue implementation and circular queue implementation. We'll compare the time complexities. And in the end of the lecture, we'll look at why is circular queue the best approach. So all these topics we will be covering in this lecture one by one. So first, let's start with introduction. Now see, we already know that in the queue, like if I take a general queue, wherein some group of students, they're standing in a queue. So in any queue you take, it will have two important things, the front and the rear. So only the front and the rear are the point of interaction. Like in a queue, you can remove an element from the front and you can add a new element to the rear. That is the NQ and DQ operation. And apart from that, we cannot touch any other object. Like we cannot add any element in the middle or in somewhere in between, or we cannot remove anything. So the only point of interaction is the front and the rear. Now if we use array, so you will get a benefit of direct indexed access. And second key feature of array is contiguous memory. Now see, this direct indexed access is something which makes array more efficient as compared to linked list. Because in array, rear you can access directly the index. But in linked list, you have to start from the beginning, because you know in a linked list, we always have to start from the head and keep on traversing till we reach the tail, the last node. So if there are millions of records are there or huge data is there, then if you implement queue using linked list, it will be very less efficient because you have to start from the beginning. So the accessing rear will be order of n, big O n. But array, because of direct indexed access, we can access both front and rear with a time complexity of big O1. It's a constant time operation. So regardless of the size of the queue, the operation will always be big O of 1. And this makes array a better choice for implementing queue, because with array, it helps in fast insertion and removal at the end. So in this lecture, we will see how we can implement a queue using array. So two approaches we will look at. We'll implement a linear queue and then we'll implement a circular queue. So first, let's look at naive array implementation. That's the linear queue. So if we talk about the structure of the linear queue, it will look something like this. Here it's an array with indexes, because we know array index starts from 0. So this is the array. Now this queue will have front and rear. Front will be basically index of first element. Rear will be index of last element. Now, if we talk about naive array implementation like a simple linear queue, this array is basically static. So it is a static array. So now we look at NQ operation in linear queue. Now we already know that in the queue, whenever we insert a new element, NQ will always occur at the rear. So NQ operation means insert a new element at the rear end. So if we look at conditions for the NQ operation, if rear is max size minus 1, because max size is the size of the array, and since the index of the array starts from 0, max size minus 1 will represent the index of the last element. So if rear is pointing to the last index of the array, it clearly means that queue is full. So the condition to check whether the queue is full or not is rear is equal to max size minus 1. Else, if queue is empty, that is front is equal to minus 1. Front is equal to minus 1 means queue is empty. So if the queue is empty, then we'll set front to be 0. Because we know that in NQ operation, we always increment the rear because NQ occurs at the end. But in one special scenario, that is if the queue is empty, because when the queue is empty, both front and rear is minus 1. So if the queue is empty, we have to set front as 0. And then we have to increment rear by 1. And after incrementing rear, the rear will point to the index where we have to insert the new element, because NQ means adding a new element, inserting a new element will insert the value at Q is the array and rear is the index, and that rear is pointing to the new index where element needs to be inserted. So these are the conditions for the NQ operation in linear queue. So let us visualize it. So suppose I have a empty queue. I know that both front will be minus 1 and rear will be minus 1. Now let us suppose I perform the operation NQ10. Now since the queue is empty already, I know that I have to update front also in this special scenario, and rear though I have to increment no matter what. So rear was minus 1, it will become 0. And wherever the rear is pointing, new element will get added there. So at index 0, new element 10 will get added. So now we have a queue with element 10 in it. Let us once again perform the NQ operation. Now let us insert 30. Now front is pointing to 0. It will not change. Just the rear will update. So rear will increment by 1. So it will become 1. So at index 1, the new element, that is the 30, will get inserted. So in this way, we can keep on adding elements. So this is how NQ operation works. Like now in our queue, we have 10 and 30. Now let us suppose I do the NQ operation 70. Front will remain 0 itself. Rear will increment by 1. So now rear will point to index 2, and that in that index 70 will get inserted. So this is the NQ operation in linear queue. Now we will look at DQ operation in linear queue. Now DQ means remove element from the queue. So DQ means remove element, and we always remove from the front in the queue. So remove element from front. That is the DQ operation. If we look at the steps, if queue is empty, that is front is equal to minus 1. That is the condition, like when the queue is empty. It means it's the condition of underflow, because DQ is not possible on an empty queue. Otherwise, first remove element at queue front, because front will be pointing to the index where element we have to remove. So the element queue front because Q is the array, friend is the index, so it is pointing to an element. We have to remove that element. And once the element is removed, we have to fill that vacant space. So move all positions, move all elements one position to the left, and we have to then decrement both pointers because we moved all elements one position to the left. We have to decrement both the front and the rear. Now let us visualize it, then it will be clear. So let us suppose I have a queue which is containing 10, 20, 30, 40. Now this is the front, this is the rear. Now when I perform the DQ operation, what will happen is that first front will get incremented and then this 10 will get removed. So, and to fill this unused spaces, we have to shift elements one position to the left. So 20 will come into the index 0, then 30 will come into the index 1 like this. So like this we have to shift. And then we have to decrement both the pointers. So DQ operation, what exactly will happen, I'll tell. So 20, 30, 40 will remain as it is, 10 will get removed, and front and rear will be like this. This is like the 50% of the DQ. Then we have to shift elements like this. And after shifting, you have to decrement both the pointers. So 20, 30, 40, because elements will be shifted one position left. This will be the front and rear will also get decremented. And this, because earlier rear was index 3, now rear will be index 2. So this is the DQ operation. If you once again perform the DQ operation, then what will happen is 20 will get removed, 30 and 40 will be shifted one position left to fill that unused space. Front will point here and rear will point to this index. Like that, we can keep on doing it and we can keep on performing DQ operation until the queue is empty. Once the queue is empty, we cannot remove any element and that will be the condition of underflow. So this is the DQ operation in linear queue. Now one very interesting observation you have to see why we are shifting all the elements by one position to the left, because it's a operation which is big O of n. This shifting operation is big O of n, because just imagine like always we have to DQ from the front and number of elements, that many shifts you have to do. So order of n. So in a linear queue implementation using array, NQ operation is order of 1. That's very good actually. But DQ operation is order of n. So the question is why exactly we are shifting? What if we don't shift? Then what will happen? So let us try to understand that. So let us suppose you have a queue like here 10, 20, 30, 40. If you remove, if you perform the DQ operation, 10 will be removed. So 20, 30, 40 will be there. Front pointer will get incremented and rear will remain same. Now what is happening is that if you don't shift elements, then this position is always unused, because insertion in the queue always occur at the rear. So this space, this vacant space is unused. In the queue, we can never use it, because if whenever you perform DQ operation, you will just keep on creating unused spaces. So we call it the issue of unused spaces. So linear queue suffers from this issue. And to save the space, to save the unused space, we have to perform the shift operation. And because of that, the time complexity of DQ becomes big O of n. Because if you don't perform the shift operation, then the DQ operation will be big O of 1 only, which will be very efficient. So here there is a trade-off between space and time. If you can afford space, then no need to shift. Then DQ operation will also be big O of 1. But in embedded systems or in mobile computing, like some chip level programming you are doing, their space constraint is there. So there you cannot afford to waste space, and then you have to perform the shift operation. So the idea is that this linear queue, although it's very simple, but it is not that efficient when it comes to real-time systems or competitive programming, because of the issue of unused space. And if you resolve that issue, then the time complexity will be big O of n. Then the time complexity will be time complexity of DQ will be big O of n. Now we'll look at efficient circular queue using arrays. So now we'll implement circular queue using arrays, and definitely it is more efficient as compared to linear queue, because circular queue takes care of the problem of unused spaces. So first let's understand the structure, or to be more precise, let us call it the concept. Like the concept of circular queue, like what exactly it is, how the circular queue will look like. So circular queue looks something like this. So here also we have like the front and the rear. So front is basically the index of the first element, and rear is the index of last element. Now initially when the queue is empty, both front and rear, they will be -1. Now this circular array, it makes use of something called as modulo arithmetic. So the basic idea of modulo arithmetic is that new index is equal to old index plus 1 modulo max size. So this will enable this circular feature, because whenever you are doing the modulo with the max size, after a point of time, it will keep on repeating. For example, let us suppose max size is 5 and old index is 4. Then new index will become 4 plus 1 modulo 5. 5 modulo 5, it will be 0. So new index will point to 0. Because if I talk about indexing, it will look something like this. So this is the concept of circular array. So circular array, in many way it is similar to linear array. The only main concept is the modulo arithmetic. Modulo arithmetic helps us in achieving that circular feature, because in circular array, looking at it, it's very clear that rear can keep on iterating. Like let us suppose if the rear is here, it can go here also. Like it can keep on iterating. And because of that, there is no issue of unused spaces. All the spaces we can make use of. That very soon you'll get a feel of it when we'll discuss the NQ and DQ operation. Then you will get some clear understanding. Now let us discuss NQ in circular queue. NQ operation. The concept is same, inserting a new element at the rear. If we look at the steps, so first you check whether the queue is full. If it is so, then we cannot insert a new element. It will be overflow. Then check if queue is empty. Because if the queue is empty, that is front is equal to -1, then we have to update front to 0. And then you update the rear. The formula would be rear is equal to rear plus 1 modulo max size. And then insert element at queue of rear. So this is how the NQ operation in circular queue will be done. Now one more very interesting observation, like what is the condition for overflow? Like how we will get to know whether the queue is full. So the condition for that is rear plus 1 modulo max size is equal to front. Because rear plus 1 modulo max size, if it becomes equal to front, it means rear has reached the front. It means the queue is full. So this is the condition. Rear plus 1 modulo max size if it becomes equal to the front index. So that's the condition for overflow. Now let us simulate it. Now I have a queue like this. It's an empty queue. So both front and rear is -1. Now let us suppose I perform NQ10. And what will happen is in this queue, since the queue is empty, first I will check overflow condition, no overflow, because queue is empty. So if the queue is empty, we have to update front also. So front will be 0, like front will point to index 0. And then we have to update rear, we have to increment it. So rear is rear plus 1, that is -1 plus 1, that's 0. Modulo max size is 7 in this scenario. Total 7 elements it can hold. So 0 modulo 7 is 0 only, so rear will be 0. So both front and rear will point to index 0 and 10 will be stored over there. Now in the same queue, when you perform NQ20, what will happen is front will remain the same, rear will get updated by 1. So rear will be the previous value of rear, that is 0 plus 1 modulo 7. So that is 1. So rear will point to 1, and wherever the rear is pointing to in that position, in that index, new element 20 will get inserted. So this is how the NQ operation will work. Now let us suppose we do NQ30. Now once again, front will remain the same, rear will update. So the old value of rear, that is 1 plus 1, 2, 2 modulo 7 will be 2. So at index 2, 30 will get inserted. So once again, we'll perform the NQ operation. Now let us suppose 40 we want to insert. Front will remain as it is. Rear will get updated. So old value it's 2, 2 plus 1, 3, 3 modulo 7 will be 3 itself. So rear would be 3 and 40 will get added at position 3. Similarly, 50 will get added, 60 will get added, 70 will get added. Now when I added 70, so rear will be at position 6, index 6. Now what will happen is, now let us suppose I want to insert 80. So rear plus 1 modulo max size. So 6 plus 1 is 7. 7 modulo 7 will be 0 and it will be equal to the front. So overflow condition will be met. So when NQ80 I will do, overflow condition will be met. And it is evident also, like looking at the visualization, we can see that the queue is already full. So that overflow condition and no NQ will be done. So this is how NQ operation works in a circular queue. Now we look at DQ in circular queue. So DQ means removing the first element, removing the front element from the queue. So DQ operation removes the front element from circular queue. If we look at the steps, so first we have to check whether the queue is empty. If it is so, then it will be underflow because we cannot remove element from an empty queue. If the queue is not empty, then remove the element at queue front. If removing last element, and how we will know about it? Because when you remove the last element, front and rear will become equal. And in that scenario, reset both front and rear to -1. Front is equal to rear is equal to minus 1. If you're not removing the last element, it means whenever we remove the element, we have to update the friend. Else, update friend. So in circular queue, the update logic will have the modulo arithmetic. So friend is equal to friend plus 1 modulo max size. Now here also let us try to understand the underflow condition, like how we will get to know whether the queue is empty, and that is friend is minus 1. If friend is minus 1, then definitely the queue is empty. So whenever you are performing a DQ operation, first check the value of the friend. If the value of the friend is minus 1, it means the queue is already empty. We cannot DQ, so we'll return underflow. Then if friend is equal to rear, you are performing the DQ operation and you found that front and rear both are equal. It means that queue contains only one element, because whenever there is only one element is present in the queue, then both front and rear will be equal. It means we are removing the last element. And in that scenario, you have to reset. After removal of the element, you have to reset front and rear to minus 1. Otherwise, if front is any other value, then you have to update the front. Like you remove the element pointed by the front, contained by the index front, and then you update the front using this formula. Front is equal to front plus 1 modulo max size. It's the basically modulo arithmetic we are using. Now let us visualize it. So let us suppose we have a queue like this, and let us suppose it already has some elements like this. Now front is 0 and rear is 3. Now when you perform the DQ operation, the front element should be removed. So front is 0. So initially front is pointing to 0. Then what will happen is that whatever element is contained at index 0 pointed by the front, it will get removed and front will get updated. So front will become previous value of front plus 1, that is 0 plus 1, 1 modulo 7. So 1 modulo 7 is 1. So front will be 1. Now front is pointing to 1, index 1. Now similarly, once again, you can perform the DQ operation. So the index pointed by the front, that is the index 1, the element will be removed from there and front will get updated. The previous value of the front is 1, so 1 plus 1, 2 modulo 7 is 2. So front will become 2. Now once again you perform the DQ operation. So the index of the front is 2, element from there will be deleted, front will be 2 plus 1 modulo 7, so 3 modulo 7 will be 3. Once again we'll do the DQ. Now here one very interesting observation. Now you can see that front and rear both became equal. It means we are removing the last element. So when you remove the last element, you have to update both front and rear to minus 1. It means the queue is empty. So this is how the DQ operation works. Now one more very interesting observation in DQ. Like see, let us suppose I have elements like this. So initially 10 was there. If I remove 10 also earlier, here there will be no problem of unused spaces, because when you will add element, like let us suppose you are adding elements, you are performing NQ operation. So rear will get updated, rear will get updated, rear will get updated. Now automatically this space will be used because rear will get updated and new element will get added here. So this space will be utilized. So in circular queue, there is no problem of unused spaces, and because of that, no need for shifting elements. And because of that, in circular queue, both NQ and DQ operation are of order 1. And hence, circular queue is more efficient as compared to linear queue. So this is the DQ operation in circular queue. Now we look at time complexity comparison. So operations, we have NQ, we have DQ. So in linear queue, we saw that NQ operation is big O1 and DQ operation in linear queue is big O(n). Because in linear queue, whenever we perform the DQ, to avoid unused spaces, we have to perform the shift operation. But in circular queue, nothing of that sort. So both NQ and DQ, big O(1). If I talk about space use, space complexity, so linear queue is inefficient because of unused spaces, but circular queue is highly efficient. So very easily we can see that circular queue is much more efficient as compared to linear queue. So why is circular queue the best approach? Now you already got the answer. Because in circular queue, all the operations are of order big O of 1. And it is very powerful actually. Because just imagine you have millions of records. If you implement it using a circular queue or circular array, like circular queue in array, not linked list, then you can perform operations on that queue with the order of big O(1), like constant time operation. So that's a very, very powerful feature of circular queue using array. Because if you use linked list, then to access the rear, you have to iterate, and that will be a very expensive operation. Because in queue, whenever you have to perform the NQ operation, you have to NQ at the rear. So in linked list, you have to reach there. So to reach the rear, no direct access is available in the linked list. But in array, direct access is available. And because of that, no need to iterate from the beginning. Directly I can access, I can get to that point. And hence, circular queue is the best approach. And that's why circular queue, you see lots of applications in operating system. Like in operating system scheduling, we make use of the queue, and circular queue is what is used. In networking, especially the buffers, networking buffers, message queues, in multi-threaded systems, queue are used. Circular queue is used. So friends, finally we completed this lecture, implementation of queue using array. I hope you liked it. You learned a lot. So do subscribe to this YouTube channel for more such interesting lectures, and do share this lecture with your friends. You share it in your circle so that they can also get benefited from it. If you want to discuss anything with me, you can drop in a comment. So thanks for watching. Thanks for your time.